n functionally dependent instances of motion that are in involution, where n is the number of degrees of freedom of the system. And we then say that a system is superintegrable if it emits more than this n constants of motion for integrability. There is a notion, though, of maximally superintegrable, which is given by 2n minus 1 integrals. And we can also define a couple other specific classes of superintegrability, one being minimally, which is just one extra, and quasi-maximally, which is one less than maximally, which will be the main focus for this talk. And so, but QMS systems are interesting because they're still highly symmetric. Like a maximally, they just have one less integral, but they can arise very naturally from many models. And importantly for this talk, they can be constructed very systematically through the coalgebraic methods. Now, to discuss these coalgebra methods, we first need to understand the notion of a coalgebra. So a coalgebra is in some sense the dual notion to an algebra. Instead of looking at products, we focus on a coproduct, a map that sends A to the tensor product with itself. And this map also must be co-associative and an algebra morphism in the way described in equations 1.2 and 1.3. And operationally, this coproduct allows us to lift symmetries or conserve quantities from a single site algebra to multi-site algebras or tensor products from many body systems in a way that's recursive and consistent. This lifting is kind of like the engine behind this construction process to get this many integrals of motion. Now, by iterating this coproduct, we can define higher order or nth coproduct maps that allow us to naturally study these many body systems. And there's two useful recursive conventions. For this, you can do it from the left or from the right, denoted the left mth coproduct and the right mth coproduct. But more specifically, the left mth coproduct acts on the first m sites in the n body system, and the right mth coproduct acts on the last m sites in the n body system. Now, these two recursive choices produce two chains of conserved quantities or integrals when applied to the Casimir elements, obviously one from the left and one from the right. Then these two families of integrals give us exactly the required 2n minus 3 integrals for a QMS system. And remembering that the last integral in the system comes from the Hamiltonian itself, giving us the required 2n minus 2. And then this construction of higher order coproducts and their applications to integrable and superintegrable systems was first kind of pioneered by Ballesteros and Ragnisko in the 90s, where they realized that coalgebra structures provide a natural and unifying framework to generate these constants of motion or integrals for multi-particle systems, allowing us to extend these integral models to higher dimensions in a very controlled and uniform manner. Their key insight, I guess, was that by iterating the coproduct across a many-body system, you automatically produce these integrals that are in involution with each other. In other words, finding the superintegral systems by chance, instead of finding the superintegral systems by chance or finding them on a case-by-case basis, you can construct them more in a more controlled way, more systematically, just from the algebraic structure itself. And that laid the groundwork for this left and right coproduct conventions that we use today. So now, why should we study QMS systems when they're not quite as nice as maximally superintegrable systems? Well, there's a couple reasons. First is that with just one less integral of motion, they're still highly symmetric and have a very rich dynamical structure worth studying. And the coalgebras give us such a nice and easy approach to uncovering these systems that we don't have to go looking on a more case-by-case situation. These integrals then can also explain spectral degeneracies and hidden symmetries of well-known models, and they can naturally connect to things like Ricard and Wilson polynomials in special function theory. A couple examples of QMS systems that can be studied are given here. Firstly, the Chmorodinsky-Winternet system. It has ND generalizations whose separability and integrals follow from the coalgebra symmetry. The Kepler-Coulomb systems, these are classical n-dimensional generalizations of the Kepler problem. They're using the coalgebra construction, you can uncover the hidden SON+1 symmetry, and then you can generate conserved quantities associated with the Laplace-Runge lens vector and angular momentum. And then the Higgs oscillator can be regarded as a nonlinear deformation of angular momentum algebra with a curvature-like parameter given by a delta. And now it's important to note that a lot of these systems and types of systems are actually known to be maximally superintegrable, but it is still possible to construct this, the 2n-2 integrals through this coalgebra approach, which can be quite helpful. And now in practice, this construction has the following process. We first determine the Casimir invariant of the underlying algebra from the model you're looking at. You then apply all the left coproduct maps, all n-1 of them, to this Casimir to obtain a chain of integrals. We then do the same for the right coproduct maps, giving us another n-1. And so this would give us 2n-2, which plus the Hamiltonian would be maximally superintegral. However, if you notice that the nth left and right coproduct map both act identically on this entire space, we see that that's clearly not functionally independent. And so we're left with the desired amount of integrals for a QMS system. Now, because the coproduct is an algebra homomorphism and is co-associative, the constructed quantities will often Poisson commute or commute in the appropriate quantum algebraic sense, producing integrability structures in a nice way. Right, but when we take the bracket relations, the Poisson brackets or the commutators of these integrals built from this approach, they often don't close in a nice linear way. They often form nonlinear, quadratic, or polynomial algebras. One of the most important examples of which is the Ricard algebra given by Rn. The Ricard algebra is a non-commutative quadratic algebra generated by three elements, let's say K1, K2, and K3, with defining quadratic relations given in equations 211 to 213. Now, it first appeared in recoupling theory of SU11, and it has been understood since Shedinov in the 90s that the families of orthogonal polynomials in the ASCII scheme, like things like Ricard, Wilson, and ASCII-Wilson polynomials, can be organized and studied through quadratic algebras. Roughly speaking, the generators of these algebras are realized as differential or difference operators, depending on the family. And these operators have the polynomials as eigenfunctions. For example, the Ricard algebra has Ricard polynomials as the eigenfunctions. Then the Ricard algebra, which denoted R3 or Rn, depending on the rank, is the typical prototype example of these quadratic algebras. Like I said, its main role is the encoding the algebraic structure of the Ricard polynomials, but it shows up in a lot of different areas. And sorry. The important part for this talk is how it shows up in superintegral systems. For example, if you realize SU11 in terms of a single oscillator, and then the total Casimir turns out to be nothing but the Hamiltonian of a generic superintegrable system on the two-sphere. From this perspective, R3 is exactly the symmetry algebra of that Hamiltonian. And when I should preface that when I say symmetry algebra, I'm referring to the algebra generated by the integrals from this coalgebraic approach. So you can see that the Ricard algebra kind of sits right at the intersection of many different subjects, from orthogonal polynomials, where Ricard polynomials are the eigenfunctions, from rep theory and the recoupling problem, and then in mathematical physics, where it comes up as the symmetry algebra of many superintegrable models. This is kind of why we say that the Ricard algebra acts as a unifying structure, because it explains these very different appearing problems like polynomials, recoupling, and integral models that are all actually facets of the same algebraic object in some sense. Now, to really make this more concrete, let's have a look at an example of where the Ricard algebra arises. So if we consider 3 copies of the SU2 Lie-Poisson algebra with generators Ji alpha, then following the procedure laid out by Latini in one of his papers, we can construct these integrals of single site, 2 site, and the 3 site Casimir operators, where alpha in these equations just represents what site that operator is acting on. And then we can compute the Poisson brackets of these 7 integrals and find that the only non-zero Poisson brackets are coming from pairs of 2-site Casimir operators given in 215. And we can also then show very easily that the bracket relation for any pair of these is actually the same up to a negative sign. So we can define this as a new generator of the algebraic substructure, which will denote F. Then computing the Poisson brackets of F and the 2-site integrals, we find these quadratic relations in terms of all other integrals of motion. This is a clear exhibit of the classical realization of the rank 1 Ricard algebra, as was seen by Latini and others in 2019. Now, let's go on to what I'm working on, the current direction of my research. So my research is all based around applying this QMS construction to algebras in 3, 4, or even n dimensions. And in the classical Poisson setting, I've been studying the substructures of the SU2 in dimensions greater than 3. But my main focus as of late has been with so-called quantum algebras, or quantum deformations of algebras. and studying how this affects the underlying symmetry algebra, especially in cases where the underlying symmetry algebra was the Ricard algebra. Now, to understand this notion of quantum algebra, I'll introduce two examples here that I've been considering. The first one is often referred to as the standard or the Q deformation. So we've got the standard deformation of the Lie algebra SU2, and we can see that the commutation relations are deformed by this Q bracket that's given in equation 2.22. But not only are the commutation relations deformed, we also deform the coproduct map in 221 by this same factor of Q. And it's important to note that this algebra is deformed in such a way that if we take Q equal to 1, we return the original algebra. And so this is actually a deformation of the universal enveloping algebra of SU2. And then the algebra SUQ2, which we've constructed here, is often comes up as the underlying algebra for many Q-deformed spin chain models. The main one that I've been focusing on is the so-called Q-deformed Kittel-Shaw model, which was first introduced properly by Ballesteros in February this year. And then the second example of a quantum deformation is the so-called non-standard or Jordanian deformation. The one I'm looking at being the Jordanian deformation of SL2R, the Lie-Poisson SL2R. And then this type of deformation, it has the same deformed coproduct map. If you imagine sending Q to e to the power of z, it's the same deformation. However, the bracket relations are now deformed by these hyperbolic trig functions instead of the Q bracket. And an important thing to note is that with these non-standard ones in particular, computing the symmetry algebra, or the closure of the symmetry algebra to be specific, is very computationally heavy, even when using Mathematica. And so it can be often very useful to employ a symplectic realization so that we can express all of our integrals in terms of their canonical generators, the position and momenta. And then once the closure of the symmetry algebra has been confirmed with the symplectic realization, we can then go and check that it follows the same structure without the symplectic realization. So, as I alluded to before, when studying the closure of these symmetry algebras and the functional independence of the integrals, the work becomes extremely computationally heavy. And so it essentially becomes, in particular, when you're working above degree 3 and with a quantum deformation. So we're essentially required to employ computer algebra software. In my case, I've been using Mathematica, and in the Lie case, the package NC Algebra. And then from that point, Mathematica is essentially used for every step of the process, from computing the commutators or Poisson brackets to testing the closure or testing the functional independence of the integrals in both the deformed and undeformed case. So overall, my project's aiming to combine algebraic structure with physically meaningful models and expose how the deformations of the underlying algebra via those deformed coproducts and deformed commutation relations give rise to the new families of QMS systems. So to wrap up, we started with this idea of a coalgebra symmetry as a systematic way to build up the quantum and classical systems with many conserved quantities. This method then lets us construct the whole families of QMS systems in arbitrary dimensions by taking the coproducts of the Casimirs. And again, to reiterate, the power of this approach is that you get the whole 2n minus 3 or 2n minus 2 integrals of motion essentially directly. We then looked at the Ricard algebra, which is, I guess, a beautiful example of how special functions, algebra, and physics can all meet under one structure. And it can explain many of these areas by linking back to one system. And then again, to reiterate, it can generalize to higher rank cases through this coalgebra picture. So I will stop there. Thank you. I'm happy to take any questions.